Now, today we are going to be discussing buses. A bus is basically multiple signal lines used for communication. Now, there's generally three types of lines in a bus. There are the control lines, the address lines, and the data lines. Now, some types of buses are what are called multiplexed. In a multiplexed bus, the address lines and the data lines are shared. They use the same lines for both address and data. One clock cycle will have the address, the next clock cycle will have the data for that address, that sort of thing. Now, these are typically shared for multiple devices. This is how you can have multiple devices communicating with one CPU. An example of a bus would be the Universal Serial Bus, or USB, is a commonly used bus. Among the buses that are most commonly used are the memory bus, and the I/O bus, input-output bus. The memory bus gives CPU access to memory. I/O bus gives CPU access to input-output devices. Input-output devices might include hard drives, printers, the USB. You'll have multiple devices on the I/O bus. The processor that we're going to be studying has let's see here, it has 4 buses. Has a data, memory, I/O, and program. That's right, it has a program bus. The data bus is used to shuffle data around within the processor. The memory bus is just for accessing the RAM memory. The I/O bus is for accessing the peripherals that go in for input and output on the device. And as was discussed in a previous lecture, this processor is a Harvard architecture processor, so it has a separate memory map for the program data, or for the program instructions. So it has a separate bus for the program memory into the CPU. Now you might raise the question, how do you control who has the bus? Bus arbitrators control the bus. This will, yes. Sure. All right. A bus arbitrator controls the bus. You can't have two devices or two peripherals or what have you trying to use the bus at the same time. You'll get situations where the data will get corrupted by data from one device will be corrupted by the data from another device, that sort of thing. Or you'll get a situation of short circuits within the processor if one device tries to pull a data line, for example, high, while another one tries to pull it low. That'll create a short circuit between the two devices, and things start burning up. So you have to have a bus arbitrator that controls who has the bus at any given time. On the bus, you'll have, say you have two data lines. Device 1, device 2. And they have access to the bus. If this one goes high, this one goes low, it'll create a short circuit. Things start burning up. Not a good thing. So what you'll have is in the digital logic review, we talked about the tri-state buffers. A tri-state buffer will turn off, and this will be the control lines, and these are the data lines. What you'll have is the control lines from the arbitrator selecting which device has access to the data lines and address lines as well. I'm just simplifying the diagrams for brevity's sake. But these will be cut if Device 2 has control. This line will be high and this line will be low, cutting off access, cutting off these connections here and allowing data to flow from device 2. That is a big part of what tri-state buffers are used for, accessing buses. So basically in the control lines, the devices will have a request line going to the bus arbitrator, and the bus arbitrator uses whatever logic it employs to determine it will have access to the bus at any given time, and will send the appropriate signal to the interface between the device and the bus to give them access. So let's see here. Don't really have much on buses. And I guess we can move right along to some data structures. Who here has not had data structures as a class? Okay, good chunk of you. Okay, I'm just going to use the basic data structures that we'll be using in the processor. Data structures class will go in more depth on how to implement these and how they work internally, that sort of thing. But first off are arrays. Now you've probably in CS1 or 2 dealt with arrays, and they are a linear structure. Start with it's indexed, starting at 0. They have the 3 things that they have that you have to keep in mind. They have a base address, element count, and an element size. You need all of these to know how to access the elements in the array. So the size of an array is calculated by the element count times the element size. Yeah. Thanks. My spelling isn't always perfect. My hand gets ahead of my brain. Yeah, indexed at starting at 0. But the size of an array is the element count times the element size. I'm skipping letters again. Count times size of element. Now the location of an element is a little bit more complex. Not much, but the location is the base address plus element number times size. Element size. So you can calculate quickly and efficiently the location of a element if you know the element size and the base address and the element number that you're looking for. So that is how they work so quickly, as opposed to a list or stack, which we won't get into lists, but we'll get into stacks. Element that you have to go through each element from the beginning to get to the element that you need. Arrays are much quicker. It takes just that one calculation to find the address of the element that you're looking for, and then look up that element. But as you can imagine, example, we might get into this in the latter half of the semester. So you have 16 elements. Each element is 2 bytes. And the base address is 0x4000, I think, is the base address of the RAM and the processor we're using. So if you need element 0 is at 0x4000. 1 0x4002. 2 0x4004. See how I'm getting that? Each element is 2 bytes. So you multiply 2 times the element number add that to the base address, and that's the address that you get for the particular element. One way to do the third programming project is to create an array in memory with different values and accessing those different values depending on the input from the user. That's one way to do the project. But we'll get to that later on if we get that far. Now the stack. The stack is a built-in data structure. It's also linear. And its starting address is typically the highest address in RAM. So and it builds down from that highest RAM location. The stack pointer points to the top. It points to the top of the stack. The stack pointer is a dedicated memory address within the processor. And think of a stack as a stack of plates. You can put a plate on top, take a plate from the top. But you can't get to the plate that's underneath unless you take everything off the top until you get to the plate that you want. Okay? So there's two operations that you can do. Push and pop. Push puts a data in the location pointed at by the stack pointer. Then it decreases the stack pointer. So you have the stack here made up of these various elements. So that's the top of the RAM. The stack pointer points here. When you push a value onto the stack, you put the data here, and then move the stack pointer down. Push again, and it'll put the data here, and then move down to here. So the stack pointer is pointing at the memory location of the next pushed value. Now pop increases the stack pointer, then gets the data. So if it's pointing here and you pop instead of push, it'll increase the stack pointer and get the data at that memory location. So you push onto the stack and pop off of the stack. Because of this, it's yes.
I know you said it's that you can't access. Have to start things up.
Yeah.
So with the pump out of that. So wouldn't the value at the top go first?
No. The stack pointer, as the I should. The stack pointer, at this point, the stack pointer is pointing here. Each time you push, it decreases the stack pointer. It moves the stack pointer down. So it's always pointing to an empty slot. Does that make sense?
I get that for the push.
The pop will then move up here, move the stack pointer up here, up one, and then gets the data that the stack pointer is pointing at. Okay? So it's a first in, last out data structure, not random access. You can't, when the stack pointer's way down here, you can't get to the data at the top of at the bottom of the stack, top of the memory, until you've popped everything off in between. So this is used for one of the important ways, purposes of this is to, when you have a interrupt, for example, you push the program memory location onto the stack. Then you jump, jump to the interrupt handling routine. Handle the interrupt. And then pop the value from the stack onto the program counter. That's program counter. So when you do a subroutine or a function call, you push the location of the program counter where the program counter is in the program memory. Then jump to the function, the line, the location of the function that you're calling. Do the function, and then you pop the value that you pushed onto the stack before back onto the program counter, and it will resume operations from that point. This will probably make a little bit more sense when we get into the programming aspect of the processor. Or does this does this make a little bit of sense as it is? Kind of. Yeah, that's what the internal stack is used for primarily, is pushing a program counter. I should. But yeah, it just pushes the program counter, jump to the handling routine, and then pop the program counter back on, from the stack back on into the program counter. So, and we'll also get into what an interrupt is, like a little bit there, a little bit later. Actually, I might be getting into that sooner than I thought. Okay. Gonna call it a day for here, but we are going to start working on looking at the processor and the technical documentation for the processor. Go ahead and download the documentation from Canvas. It's in the files section of Canvas. It's the AVR 128 DA 48. And there'll be some other numbers in the file name as well. But that's the name of the processor that we are going to be using. So download that technical reference sheet. Don't be intimidated by its size. It's only a 684 pages. Oh, they get bigger than that. But we won't be reading it all. I've been using the processor for years, and I haven't read it all. But download it. See if you want to dip into it. But we will be looking at it in more detail on Wednesday. In the meantime, have a good day. Stay warm.